Hello everyone, my name is Zhengang Li. I'm a PhD student from Northeastern University. It's my great honor to present our paper, NPAS, a compiler-aware framework of unified network pruning and architecture search for beyond real-time mobile acceleration. Nowadays, machine learning is becoming increasingly popular. Deep neural networks have emerged as a fundamental element in machine learning applications due to its high accuracy and excellent scalability. Many new applications such as self-driving, resolution upscaling, and speech recognition are highly relying on DNN. To promote portability and flexibility, more applications are now targeted on resource-limited devices, such as mobile phones. However, deploying DNN models on resource-limited devices is a challenge. The main reason is that people always want to have better DNN accuracy, which leads to a larger and larger model size. First, the huge model size guarantees the good performance for the DNN models, but it is very challenging to fit such huge model on a mobile device. Second, a deep and large model usually requires a large computation resource, which is hard to be obtained from a mobile device. For specific situations like auto driving, we need the inference process to be fast and the size of model to be small, in order to support the real-time requirement. We need to simplify the computational complexity as well as keep the model's robustness and accuracy. To realize this, model compression is a good choice. For network pruning, it can be categorized according to pruning schemes. There are three major groups in the previous work: unstructured pruning, cross-grain structured pruning, and pattern-based pruning. Unstructured pruning, as shown in the first row of the figure, removes weights at arbitrary position. Though it can significantly decrease the number of weights in DNN model, the resulted sparse and irregular weight matrix hurts the parallel implementation of the hardware, results in limited acceleration. To overcome the limitation of unstructured pruning, the cross-grain structured pruning has been studied in many works. As shown in the second row of the figure, the cross-grain structured pruning removes the whole filters or channels in the model. The pruned model still remains the network structure with high regularity, which can be utilized by the hardware. But the downside of the cross-grain structure pruning is the obvious accuracy degradation by removing the whole filters or channels, which limits model compression rate. For the pattern-based pruning as shown in the last row of the figure, it assigns a pattern from a predefined library. For each kernel, it can be either completely removed or reserves 4 non-zero weights from the assigned pattern. Pattern-based pruning can simultaneously achieve high accuracy and high inference acceleration with the aid of compiler. The limitation of the pattern-based pruning is that it can only be used in 3x3 count layers in current work. Besides the network pruning, the neural architecture search is also a good way to obtain lightweight model. There are many representative methods of NPAS, like reinforcement learning methods, evolution methods, one-shot training, and gradient-based methods. Some recent work like ImageNet, FBNet, and proxyless NAS realized the importance of hardware co-design and incorporated the inference latency into NAS, which is more accurate than the intuitive volume estimation like flops. However, none of this hardware targeting work fully exploit the potential of compiler optimizations or explore the benefits of weight pruning. This motivates us to investigate another dimension of model optimization, that is, compiler-aware latency-constrained architecture and pruning code search. Here are the contributions of our work. First, we propose a general category of fine-grained structure pruning applicable to various DNN layers, and a comprehensive compiler code generation framework supporting different pruning schemes. We bridge the gap between model compression and NPAS. Second, we develop a compiler-aware framework of joint network pruning and architecture search. Maximizing accuracy will satisfy inference latency constraint. The third, we design a systematic search acceleration strategy, integrating pre-trained starting points, fast accuracy and latency evaluations, and Bayesian optimization. The last but not least, our NPAS framework achieves by far the best mobile acceleration with high model accuracy. As mentioned in our contribution, we propose two new pruning schemes that can be applied to various DNA layers. The first is block-based pruning as shown in Figure B, which is applied on FC layers. The entire weight matrix is divided into a number of equal-sized blocks. Then the entire columns and rows of weights are pruned within each block. Compared to the cross-grain structured pruning, block-based pruning provides a finer pruning granularity to better preserve the DNA model accuracy. With an appropriate block size selected, the remaining computation within a block can still be parallelized on a mobile device with the help of compiler. As a result, block-based pruning can achieve comparable hardware inference performance as cross-grain structured pruning under the same overall pruning rate. Inspired by block-based pruning, as a second proposed pruning scheme, we developed block-punch pruning scheme tailored for the count layers, which can be accelerated using the same compiler optimization. As shown in Figure A, block-punch pruning requires pruning a group of weights at the same location of all filters and all channels within a block to leverage hardware parallelism from both memory and computation perspectives. With effective compiler-level executable code generation, high inference acceleration on mobile can also be achieved. Furthermore, we develop a comprehensive compiler-based automatic code generation framework supporting the proposed block-punch and block-based pruning schemes in a unified manner. It also supports other pruning schemes such as unstructured pruning, cross-grain structured pruning, pattern-based pruning. In fact, unstructured and cross-grain structured pruning are just special cases of block-punch pruning. The former has the block size of 1 by 1, and the latter has the block size of whole weight matrix or tensor. And based on this framework, we further test the impact of different block sizes. For example, as shown in the figure in the right up corner, block size 8 by 4 gets the best combination of latency and accuracy. In the later experiment, we use this size as our hyperparameter. This figure shows the overview of our compiler code design system. We are using a very standard and comprehensive compiler design flow. First, from the training, we got a sparse neural network which has different pruning schemes. Then, we will get a graph-based representation of the compressed DNA. From the compressed model here, we conduct compiler-based optimizations including computation reordering, auto-tuning, layer fusion, so on and so forth. And what we generate from this step are the executable codes. For example, the C++ code for the mobile CPU, OpenCL and OpenGL code for mobile GPU, and together with our compact model storage. Then the executable codes can be directly deployed on the mobile devices for application. Here I'd like to introduce two important mechanisms which have close relationship with our proposed NPAS framework. The first is the layer fusion mechanism. In our compiler optimization, we incorporate a layer fusion technique to fuse the computation operators in computation graph and efficiently reduce the inference latency. The reason is that layer fusion reduces not only the memory consumption of intermediate results, but also the number of operators. Here, the figure shows 7 fusion candidates for 2 sections of a computation graph. We use case 3 as an example. Before fusion, the number of original layers and algebra operators are 4 and 5 respectively. By grouping the computation, after fusion, this whole fused block can be treated as one layer with 3 operators. With the reduction, the computation overhead can be reduced efficiently. For auto-tuning part, DNA model execution usually involves many performance-critical tuning parameters, such as data placement on GPU memory, matrix tiling sizes, and loop-on-rolling factors. The best suited configuration of these parameters is hard to be determined manually. In NPAS, our compiler incorporates auto-tuning as other DNA inference frameworks, such as TVM. To facilitate an efficient auto-tuning process, we utilize the genetic algorithm to explore the best configuration automatically, which makes it possible to return the latency measurement to our search process. Here, Figure 4 shows the proposed NPAS framework to take advantage of recent NAS results and accelerate the NPAS process. We start from a pre-trained DNA model and go through three phases as shown in the figure. Phase 1 is the replacement of mobile unfriendly operations. Certain operators are inefficient to execute on mobile devices. For instance, some activation functions, such as sigmoid, switch, require exponential computation and can become latency bottleneck on mobile inference. These unfriendly operations will be replaced by compiler-friendly operations, such as hard sigmoid and hard switch, with negligible effect on accuracy. Phase 2 is NPAS scheme search. This phase generates and evaluates candidate NPAS schemes, defined by the collection of per-layer filter types, pruning schemes, and pruning rates, and finally chooses the best suited one. Here we incorporate the overall DNA latency constraint in the reward function of NPAS scheme search. The overall DNA latency is actually measured on the target mobile CPU or GPU based on the candidate NPAS scheme currently under evaluation. We rely on actual measurement instead of per-layer latency modeling as many previous NAS work. This is because our compiler optimizations incorporate the layer fusion as mentioned, which makes the inference more efficient, but makes the per-layer latency modeling less accurate. Here we show the search space of phase 2 in table 1. The candidate filter types includes 1 by 1, 3 by 3, 3 by 3 depth-wise, so on and so forth, or even skipping the whole layer if necessary. Besides that, the NPAS agent can choose from filter pruning, pattern-based pruning, and block punch or block-based pruning with different pruning rate for each layer. As different layers may have different compatible pruning schemes, we allow the NPAS the flexibility to choose different pruning schemes for different layers. This is well supported by our compiler code generation. Here we use the Q-learning algorithm as the base technique. Epsilon graded strategy, experience replay, and Bayesian optimizations are used to accelerate this search. Besides that, we also develop a set of fast accuracy evaluation methods as shown at the left-hand side. Here, the one-shot pruning will result in accuracy degradation, but after several apples in retraining, it can distinguish the relative accuracy of different NPAS schemes. Besides that, the compiler code generation and latency measurement do not need the absolute weight values. Compiler code generation is much faster than DNA training and can be performed in parallel with accuracy evaluation. As a result, it will not incur extra time consumption to NPAS. Phase 3 is to search pruning algorithm. The previous phase has already determined the per-layer filter types, pruning schemes, and pruning rates, so that the compiler-generated code can satisfy the overall latency constraint. The remaining task of this phase is to search for the most desirable pruning algorithm to perform actual pruning and train the remaining weights. In phase 3, we compile the resulted DNA accuracy from the candidate pruning algorithms in a few apples, select the one with the highest accuracy, and continue a best effort algorithm to derive the final DNA model. Here we give part of the result of our experiment. All the experiments are on Galaxy S10 smartphone. In this table, it's obvious that we got a better model accuracy while achieving less inference latency compared with the previous work. With 77% of top 1 accuracy on ImageNet, we can achieve 6.7 milliseconds on mobile GPU and 11.8 milliseconds on mobile CPU. Here are more results. We compare our accuracy and latency results with representative DNA inference acceleration framework, MNN, PyTorch Mobile, and TensorFlow Lite on both mobile CPU and GPU. PyTorch Mobile does not support mobile GPU, so no corresponding results. 4 dense DNA models are used for the comparisons, which are MobileNet V3, EfficientNet B0, and 2 versions of shrunk EfficientNet B0. The red stars shapes the figures represent the NPAS-generated results under different latency constraints. Our NPAS results consistently outperform the representative DNA models and achieve the Pareto optimality in terms of accuracy and inference latency. With MobileNet V3 level accuracy, our inference time on mobile CPU and GPU are 9.8 milliseconds and 5.9 milliseconds respectively. With MobileNet V2 level accuracy, the inference time of NPAS solution on mobile CPU and GPU are 6.9 milliseconds and 3.9 milliseconds respectively. To the best of our knowledge, this has never been accomplished by any existing NAS or weight pruning work. This is the end of my presentation. Thanks for listening.